And hello. Today we'll be looking at symmetries and translations. So you might already be familiar with symmetries or symmetrical things, but maybe not translations. So we're going to look at firstly what translations are. Well, a translation moves an object in a particular direction without rotating it. So in this example here, the bag started here and we just moved it over here. We didn't rotate it, we didn't cut it in any way, we didn't change it anyway. It's the exact same object. It's just literally like you clicked it and dragged it over here. So that's the definition of a translation. It's a very particular thing. It's not rotating it, not cutting it up. It's literally just picking it up, moving it somewhere else. Kind of like this cursor actually. Cursor of my mouse, it's not being turned around, it's not getting bigger or smaller, it's exactly the same, it's just being moved left and right or around. So here's a bigger example of what I mean. So these are multiple translations. So you can see the arrow is moving like that. That's one translation. So it started here, it moved over here, that's a translation. Why do we care about translations? Well, as I said, your mouse on your screen, it's just moving with translations. So here's a path of a mouse, let's say. You'll notice all it is moving one translation, stops, another translation, stops, another translation, stops, and then goes over here. So this is important because this is how computer scientists and programmers and developers code objects. They don't code it as in, oh, move the mouse to this particular point, blah, blah, blah. They just say, okay, here's a translation from here to here. Then when I move the mouse over here, well, it's sending another signal to translate the cursor from here to here. So animations are just multiple translations over and over again. Now, mathematically, we use a coordinate system to know where to go. So you remember from coordinate geometry and plotting points, this point here, well, it's about 5 point something and 8.4, I'd say, or something like that. And it's what it is okay, send the cursor from this point to this point over here, which is about 11.1 to 4 point, or is it 4? Yeah, 4 point something. So yeah, what we do is we need to know these points, and that's how we move the cursor. We say, okay, send the cursor from this point to this point, then send the cursor from that point to that point. So that's 5.5, 8.5, and we want to send it to 11.1, 4.4. Let's say we had a box now, and we want to move the box somewhere. Well, what we can actually do is, instead of looking at the whole box, let's look at a particular point. So let's say this point here. And let's say I want to move the point over to this point. So at that particular point, I want to move it over there. There's your translation. So that goes along that line all the way over to there. So what happens is, instead of just, doing it out again for this point and this point and this point, all we do is just, see the way that line there, I just slided it down to here. And then I can find where this point goes to. It goes to here. So it's the exact same direction. All the points will go in the exact same direction by the exact same length. So I can just basically slide that length down to here. So I want to get to this point, and then I can find where it'll end up. I could also just slide it across to here, so I can find where this point ends up. What about this point here? I want to find where it is. Well, I could just slide this down to here, and I could find where it ends up. And then I see where the blue square is. That's the exact copy of that blue square. But instead of figuring out, okay, I need to pick this point, go across there, I need to do the exact same for this, I just slide those lengths across. So you could do this on a sheet of paper with your set squares. So if you get the length from there to there, we could just slide that length down to here and get this length, or we could slide it across and get that length. These are all the translations then of these points. And then we call this the image. So this is the original, and this would be the image. This is what's we make up after the translations. Okay, so let's look at symmetries now. So that was translations, just moving things. We're not we're not changing it anywhere, we're not rotating it, it's just moving it from one place to another. What about symmetries? So you're probably familiar with symmetrical things, so like a symmetrical face. You might also have seen this maybe in physics or science, this kind of symmetry, which we look at in a second. It's called central symmetry, and this is called axial symmetry. So why do we say axial? Well, you might remember the word axis. Remember in coordinate geometry, axis, like you have the x-axis and the y-axis. So in this case, you have an axis going down the middle of this woman's face, and anything to the left is symmetrical to anything on the right. So we say it is symmetrical. So axial symmetry, or it's also known as reflection about a line, is a reflection of an object about a line or an axis. So these are all axial symmetries. So you have a tree. So imagine if I had this cut out on a sheet of paper. If I folded this side over onto this side, it would be exactly the same. That's another way of thinking about axial symmetry. If you fold it over, it should be the exact same image. So this butterfly, if I cut it down the middle and I folded this over, it would be exactly the same. This kind of chess, kind of club looking piece, it would fold it over, it would be exactly the same. And this ornate kind of symbol, if you cut it down the middle, it would be exactly the same. So axial symmetry is just a reflection of an object about a line or an axis. So practically, going back to our coordinate system, let's say we had a triangle. And let's say we had an axis like this. So they're not always straight or horizontal. They might be at an angle. So here's an axis. I want to fold this over to here. So imagine this is a sheet of paper. I have this on this side and I fold it over. I want to get, how would I do that? This is what we call the axis of symmetry. So this is the axis we're kind of folding it over. And how do we do it? Pick a point on your object. So let's say this point. And we draw a perpendicular line to the axis. So this is at 90 degrees. This is 90 degrees, 90 degrees. So that's what we call the perpendicular distance. So that's the distance from this point to this line perpendicularly. So it's not just drawing it like any which way, it's the perpendicular distance. What I do is I just continue that line and I go out the same distance. So whatever the distance from this point to this line, I do the exact same distance from the line out, so to there. And that's where that point will end up. Let's say this point, exact same thing. I do a perpendicular line to the axis of symmetry. Then I say, okay, what's this distance here from the red dot to the line? I go out the same amount, and that's where the red dot will end up. Then I do the same with this. Perpendicular distance to there. So that's a long line there, it goes all the way to there. Continue it out, all the way out. And that's where that'll end up. And that's your axial symmetry. So if you notice, if I fold this line, imagine this is a piece of paper, or fold it, it would end up exactly here. So how do we do it with the coordinates? Remember, distance from this point to the line, distance from this point to the line, perpendicular distance now. You extend out those lines. Same distance out, same distance out. Same with the red dot, and then you just draw your triangle. Again, this is the original image, or the original object, and this is what we call the image. Central symmetry is probably everybody actually in the world uses central symmetry because it's to do with our eyes. So when we see things, you learn about this in physics for leaving cert actually. When we see things, we actually see them upside down. And why we see them upside down is this. We see something, the light comes into our eye, it hits a particular point, and then it keeps on going, and then it comes to the back of our eye. So the light from here comes down, comes down, comes down, hits here, keeps on going, comes down, goes down, goes down, and then ends up at the back of your eye, but it's upside down. And the same with the shoe. It comes up here, it comes into your eye, and then it ends up here, but that'll be upside down. So central symmetry is a projection of an image through a point. So the center of symmetry is what we call the point. So that would be here in your eye. So that's, you need to remember what that's the definition of that. So let's say we had kind of like this lightning bolt symbol. And let's say we wanted to use central symmetry through this point. How would we do it? So that's the center of symmetry. Again, let's pick a point on the object. So on the lightning bolt, pick this point. What you do is think about the eye. You just draw a line to the point. It doesn't have to be perpendicular distance or anything like that. Just draw a line to the point. Now, take note of this distance with your ruler. This is the distance from the point to the center of symmetry. Then just continue drawing that line out and go out the exact same distance. So whatever this distance was from the point to from the point on your object to the center of symmetry, go out the exact same distance. That's where your point will end up. Then do the exact same for this. So this point here, go out a certain amount, then go out another the exact same amount. Then do it for another point. And for another point. Then you can just draw your image. Now you'll notice central symmetry always flips your object. So this is your lightning bolt and it turned upside down. But it's exactly the same. It's just flipped upside down. That's what we call central symmetry. So again, I'll say how we do it. Pick a point, draw a line to the center of symmetry, find out what that distance was, then just continue that line going on out. And go out the exact same distance from your center of symmetry to a certain amount, so whatever this distance was, and that's where your point will end up. Okay, as I always do, I'll leave you with the recap questions here, and you can pause the video and do them. So, which of these transformations, A, B, or C, below will map K to L? So we have a map here, or not a map, a flag, and it goes from K to L. So the map, or the flag is just kind of been moved over here. Did it rotate? No. Was it cut or anything? No. It just was picked up and moved across. So what would that be? It's a translation. It's exactly the same. It's not flipped. It's not rotated. It's just picked up and moved along. From L to M. Now, what's going on here? Think about it. It's a reflection in a line, or axial symmetry. And why is that? Imagine if I drew a line maybe roughly there. If you folded it, so I fold this side over, it would be exactly over to M. Now it's not a translation, because if I just picked it up and put it down here, it wouldn't be the same, because look, it's rotated a bit. And it's not a point, because if I pick this point here, or any point, notice if I draw this through, and I went there, it would end up over here. And it has to be turned upside down. That's not turned upside down. What about L to N? So this to this. Well, now you notice, okay, it's not translation because it's rotated. Is it an axial one? No. I don't think there's a way I could fold it to make it to go there. But you notice, see the way it's flipped upside down? Well, that means it's central symmetry.